option is, in this lecture we'll be doing Dirac's theorem, but before proving this theorem we'll do some definitions and some preliminary results for this theorem. So we say a graph G is of order n if number of vertices in G is equal to n. Suppose there is a vertex, suppose V, and let V1, V2, so on, Vd be the vertices that are adjacent to V. So these are the sort of all vertices that are adjacent to V. Then these Vi's, V1, V2 through Vd, they are called the neighbors of V, and it is denoted by n of V, or sometimes gamma of V. So the number of vertices which are adjacent to V is called the valency or degree of V. So the size of this nV or gamma V is called degree of V. This is same as degree of V. Now if we have a graph G on n vertices, i.e. the order of graph G is n, then a vertex, suppose this vertex V1, V2 and so on up to Vn, these are n vertices, and this graph is given to be simple, i.e. it has no parallel edges or loops. So these are the vertices V1, V2, V3. So this vertex can be adjacent to all these vertices, but V1 is not adjacent to V1, because in that case this will be a loop and the graph will not be a simple graph. So degree of a vertex V1, degree of this vertex V1 is at most n minus 1. It cannot be equal to n. So next, a graph G is said to contain a Hamiltonian cycle if that cycle contains all the vertices of the graph G. Suppose G is a graph on n vertices. If we have a cycle like this, such that this cycle contain all the vertices of G, then this cycle is said to be Hamiltonian cycle in G, and G is said to be a Hamiltonian graph. Now we are going to prove this theorem by Dirac, and it states that is given by Dirac. It says that let G be a graph of order n, where n is bigger or equal to 3. That is, G has at least 3 vertices, and is given that such that delta G, which is the minimum degree of a vertex in the graph G, it is given to be bigger or equal to n by 2. That means if we pick any vertex in G, its degree is at least n by 2. It cannot precede n by 2. Then G is Hamiltonian. Then G is Hamiltonian. That is, G contains a cycle which contain all the vertices of G, i.e. the Hamiltonian cycle. To prove this result, we first claim, so this is our claim first, we claim that G is connected. Claim 1, G is connected. We prove this claim by contradiction. We assume that G is not connected. Suppose not I mean suppose G is not connected, then G has at least two components. At least two components. It may have more than two components, but if it has one component, then G is connected. So if we assume G is not connected, then it has to contain more than one component, i.e. it has to contain at least two components. By a component we mean a connected subgraph. Now let us pick the smallest component in G in terms of the vertices. Suppose G has two components, G1 and G2. Now let us pick among G1 and G2 that component which has the minimum number of vertices. Now here in our case G has more than one component, and we are picking that component which have least number of vertices. Let us pick the connected component, the connected component with minimum number of vertices. Minimum number of vertices. It is given that the minimum degree in G is bigger or equal to n by 2. Suppose if G has two components, then the component with minimum number of vertices has to contain more than n by 2 number of vertices. Hence any component of G has at least n by 2 not at least I mean this component. Hence this component of G has at most n by 2 vertices. Now we know that if G is a graph on n vertices, then the maximum degree of vertex cannot exceed n minus 1. So in this component, which is minimum number of vertices, the degree of a vertex cannot exceed n by 2 minus 1. Hence this component of G has at most n by 2 vertices, and any vertex in this component has at most n by 2 minus 1, and any vertex in this component has at most n by 2 minus 1 degree. So degree of a vertex cannot exceed this number, but it is given that the minimum degree of a vertex in graph G is at least n by 2, so that is it is bigger than or equal to n by 2. Here we have seen that there is a vertex in G with degree at most n by 2 minus 1, i.e. less than n by 2 minus 1. This contradicts the given hypothesis that minimum degree is bigger or equal to n by 2. This contradicts the given hypothesis. That delta G is bigger or equal to n by 2. Now G is given to be now G is connected. We have therefore G is connected. Now given that G is connected, between any two vertices in G there is at least one path. So we can choose a path of maximal length, of the largest length, and let us consider, let P equal x naught, x1, x2 through xl. Now this is a path between vertices x naught and xl, which is of the largest length. Let P be a path let P be a path of largest possible length. Now given that G has n minus 1 vertices, so here these x1, x2, xl, these are the vertices in G. So this number and this the length of this path is L, so this L cannot exceed n. So L is either equal to n minus 1 or less than n minus 1, because a path with n vertices has length n minus 1. So here we have L vertices, L plus 1 vertices, so the length of this path is L, because there are L plus 1 vertices, and this L is either less or equal to n minus 1. Since G is connected, with n vertices, then this L is less or equal to n minus 1, because in a graph of order n, i.e. a graph on n vertices, in a graph on n vertices we cannot have a path of length bigger than n minus 1. That is why L is less or equal to n minus 1. Now note that if L is equal to n minus 1 here, then this path contains n vertices. So G is a graph on n vertices. That means this path contains all the vertices of G. In that case, this path will be a Hamiltonian path, and the cycle which starts from x naught and ends at x naught will be a Hamiltonian cycle. So we are done in that case. If L is equal to n minus 1, we are done, since x naught, x1 through xl, x naught will be our required Hamiltonian cycle. Now if L is less than n minus 1, we should get a contradiction. So here we are given that L is either less or equal to n minus 1, so we have to eliminate the possibility that L is less than n minus 1. So we are taking here n is less than n minus 1, so we should end up at some contradiction. Since P is the maximal path, it cannot be extended to a longer path. It can not be extended to a longer path. One should note that if this is the path x0, x1, x2, xl, then x0, x1 is an edge, x1, x2 is an edge. Similarly, xl minus 1, xl is an edge. In general, note that x0, xi plus 1, this is an edge of G for all 0 less or equal to I less or equal to L minus 1. So this is our path, which is x0, this is x1, this is x2, so on. This is xl minus 1, this is xl. One should note that all the neighbors of x0 must belong to this set x0, x1, x2, xl minus 1, xl. And similarly xl, suppose x0 has a neighbor which is outside here. Suppose this is some neighbor of x0 and it is outside these xi's. So suppose this is y. So if this is so, then we have a path which starts at y and ends at L. Then we have a path of length L plus 1, which is not the case because we have assumed that this path P is the maximal path in terms of length. Similarly, XL must have no neighbor outside these vertices. So this is not the case here. So observe that neighbors of x0 and neighbors of xl. So this is a set of all vertices in G which are adjacent to x0, and this is a set of all vertices in G which are adjacent to L. So these two sets are subsets of this set x0, x1 through xl, as we have mentioned that x0 and xl cannot be adjacent to any other vertex other than these vertices because P is the maximal path. Now let us note, let A be the set gamma of x0, I the set of all neighbors of x0, and B be the set it contains those xi's such that xi minus 1 is neighbor of XL. So now minimum degree of G is n by 2, so size of A is at least n by 2 and size of B is at least n by 2. Since there is one-to-one correspondence between the vertices in B and the neighbors of XL, because for each neighbor xi minus 1 in for each neighbor xi minus 1 of XL, we have an element xi in the set B. So since minimum degree is bigger or equal to n by 2, we conclude that size of A and size of B is at least n by 2. Now we claim that claim second, x naught is not in A, because if x naught is in A, that means x naught is neighbor of x naught, i.e. at x naught we have a loop, and that is not the case. So x naught is not in A, and similarly x naught is not in B. Otherwise there is some vertex, otherwise there is some y which will be equal to x, so x0 is not in B. If x0 is in B, that means x0 minus 1 is neighbor of 0 minus 1, that is minus 1 is neighbor of XL. But that is not the case, as we have mentioned earlier that the neighbors of XL belong to this set. So XL cannot have a neighbor which is of the form x underscore minus x subscript minus 1, say y. Otherwise there is some y which is equal to x minus 1, which is in the neighbors of gamma. This is not true, since gamma of XL is subset of x naught through XL. Now size of A union B, size of A union B is less or equal to n minus is less or equal to n minus 1, since x naught does not belong to A or B. Obviously A and B, these are the vertex these are the subsets of the vertex set of G, and the size of vertex set of G is n. So size of A and B is at least n minus, is at most n minus 1, because x naught is neither in A nor in B. So this is the equality here. Now we claim that A intersection B is non-empty. For if A intersection B is empty, then size of A union B will be equal to size of A plus size of B, because they are disjoint. But size of A is bigger or equal to n by 2 plus size of B is bigger or equal to n by 2, and that is equal to n, i.e. size of A union B is bigger or equal to n plus 1, and that is not the case, because A and B are both subsets of the vertex set of G. Hence A intersection B is non-empty. And let us suppose xt belongs to A intersection B for some t. Now xt is in A as well as in B. Now when xt belongs to A, now xt belongs to A, what does it imply? It implies that xt is neighbor of x naught. This implies xt belongs to neighbor of x naught, and xt belongs to B implies xt minus 1 is neighbor of xl. This means xt is adjacent to x naught and xt minus 1 is adjacent to xl. So if we consider like this, so this is our path, this is x naught, this is x1, so on, this is xt minus 1, this is xt, this is xt plus 1, so on, this is xl minus 1, this is xl, this is x naught, this is x1, this is xl minus 1, sorry, this is xt minus 1, this is xt, and this is xt plus 1, this is xt plus 1. Let us make it up, let us redraw it. So we have x naught, we have x1 here up to xt minus 1, then xt, then xt plus 1. So this is xt minus 1, this is xt, and this is xt plus 1, so on. And then we have xl minus 1, this is xl, this is xl minus 1, this is xl. Now since xt belongs to A, that means xt is neighbor of x naught here, i.e. x naught is adjacent to x naught, that is there is some edge between xt and x naught. Similarly, there is an edge between xl and xt minus 1, so we have an edge between xt minus 1 and xt. We have eliminated the case here, the case L is equal to n minus 1, because if L is equal to n minus 1, we are done in that case. Now we have assumed that L is less than n minus 1. If it is so, since L is less than n minus 1, then there is at least one vertex, say V in VG, then there is at least one vertex, say V in VG, which is, now if L is less than n minus 1, that means in our path P, which is from x0, x1, so on, xl, this path contains at least at most n minus 1 vertices, at most, it contains less or equal to n minus 1 vertex. That means there is some vertex, that is say V, which is adjacent to some vertex here, because if it is not so, then this graph will be disconnected. as we have mentioned earlier, that between any two vertices there is at least one path, and that is the definition of this graph, connected graph, I mean. So there is at least one vertex, say in VG, such that V is not in the path P, but G being connected. V must be adjacent to some vertex, say XR, where 0 is less or equal to R is less or equal to L in P. Now we have two cases here. So this is our path. This is x1, sorry, x0, then x1, and let us suppose that here is xr minus 1, this is xr, this is xr plus 1, so on. This is xt minus 1, this is xt, this is xt plus 1, this is xt plus 1, so on. This is xl, and this is xl minus 1, this is xl. Now we have a vertex V here. Now this V is vertex to VR, so we start with vertex V and goes to XR. Then we will go to XR plus 1 through XT minus 1, XR plus 1, so on to XT minus 1. Once we reach to XT minus 1, and given that XT minus 1 is adjacent to XL, from XT minus 1 we can jump to XL, and from XL we can travel back to XT. So XL goes to XL minus 1, XL minus 2, so on to XT. Here XT minus 1 has already it shows up in this path here. So once we reach to XT, XT is given to be adjacent to X0 here, so we can jump to X0 and travel the remaining path to XR minus 1. So it is X0, X1, so on, XR minus 1. Now this path over here, this path contains L plus 2 vertices, so its length is L plus 1, but that is not possible as we have taken P to be the path of maximum possible length. So this is not the case. This won't work. This is not going to work. Now other case is that here this XR comes before XT. Now the other case is that when XR comes after XT. So here we have vertex V, so we'll start over here. This is X0, then X1, so on, XT minus 1, xt plus 1 so on xr minus 1 xr plus 1 so on xl l minus 1 xl. So in this case, so there are only two possibilities: either xr comes before xt or xr comes after xt. When xr comes before xt, we have seen that we can find a path of length l plus 1, and that is not the case, so this is not going to work. And when xr comes after xt, we'll start with vertex v, then we will reach xr plus 1 and we'll proceed till xl, so like this, and finally we reach xl. Now xl is given to be adjacent to xt minus 1, like this. So from xl we can directly jump to xt minus 1. Now we can, once we reach xt minus 1, we can travel this path backwards. So xt minus 1 goes to xt minus 2, so on it goes to x naught. Now from x naught we can jump to xt plus xt, and from xt we can go to xt plus 1, so on xr minus 1. Now this is again a path which contain l plus 2 vertices, first x naught xl and then this vertex v. So this path has length l plus 1. So again, if we denote this path by p prime, so for p prime we have two options: either p prime is this or p prime is this. In both the cases we end up at a contradiction. So l cannot be less than n minus 1, because when we chose the length of l to be less than n minus 1, for that reason we were able to choose this vertex v. If the length of path is exactly n minus 1, there would be no choice for this vertex v. So length of l is not less than n minus 1, that is l is equal to n minus 1, and when l is equal to n minus 1, we are done in that case. So our path p will be the Hamiltonian path, and this cycle x naught x1 through xl to x naught, this will be our Hamiltonian cycle. So this was the Dirac's theorem. Thanks so much.